So a weak acid, however, it barely dissociates. In fact, the majority of weak acids, they dissociate less than 5%. So that means that the majority the um, of your reaction stays as reactant and very little of it goes to product. So what you should know though is the last point here, the weaker the acid, the stronger its conjugate base. Now, be really clear on this. If you have a weak acid, the conjugate is not a strong base. Anytime of a weak acid, the conjugate will also be a weak base. Does that make sense? In fact, if you have a strong acid, like let's say HCl, its conjugate Cl minus, it's going to be an incredibly pathetic weak conjugate. So that's the only case where you could say that the conjugate of the weak base, Cl minus, is a strong acid. So the only time you can ever say that the conjugate is a strong is if the conjugate is part of CBS-PIN or the conjugate is part of one strong CalBar. Now, just to give you an example here, this is an example of a strong acid. So can you guys see how when I'm circling with my mouse or no? Kirsten, respond. Can you see me circling the HA? Okay. So here we have, prior to the reaction, all we have is a strong acid. At the equilibrium point, and I'm using air quotes for equilibrium because it's not really equilibrium, you see we have the same amount of H plus and A minus as we had HA originally, and we have none of the HA left.
Yes.
Whereas if we go to HB, which is, I don't know why they didn't call it HA again, but I guess that represents a weaker acid. If you have a weak acid, at the end, you end up with almost as much weak acid as you had originally and only a very small amount of HA and the conjugate base. So if we were comparing these two right here, we would say that the weak acids conjugate is a weak base, and the weak base conjugate is a weak acid. The only time that a weak base, I'm circling the A minus over here, conjugate is a strong is if it's one of CBS-PIN, or if we're doing the conjugate of a strong base, it's part of one strong CalBar. Now, these are some ways that we describe acid-base strength, and this is actually a really, really good table. You guys have at the top of page, I'm on the wrong page here, but I think it's page 657. Yeah, it's top of page 657. You have this. You can look at it, but I also put this online. So if your K is very large, you have a strong acid. If your K is really small, you have a weak acid. And this is just kind of reiteration. If your equilibrium lies far to the right, you have a strong acid. If it lies far to the left, you have a weak acid. What's kind of important for you guys to realize is that what defines an acid is how easily it gets rid of its hydrogens. So if something doesn't dissociate very well, it's not very good at getting rid of its hydrogen, which means it's going to be a weak acid, which also means that you're going to stay mostly with the weak acid on the left-hand side, which is why your equilibrium is far to the left. Now, the other thing to be aware of here is this, and this is kind of cool. If you compare your H plus at equilibrium to what your initial amount of the acid was, and let me point out that little zero. See that little zero right there? Yep. That means not. I don't know why they call it not instead of whatever, but that means initial. So anytime you have a little not symbol, that means the initial amount. So if you have the initial amount of your acid for a strong acid, at the end will be equal to the H plus concentration you have. Whereas if you have the initial amount of a weak acid, you're going to have way more of the weak acid at the end than you do the H plus, because quite simply the weak acid over here does not completely dissociate. And similarly, if you compare the conjugate bases, the conjugate base of a strong acid is pathetic. Now, H2O, we consider H2O to have kind of a neutral, be neutral, and it have a Ka of 1.0 times 10 to the negative 7. If you're wondering how I got that number, you realize that if you took the H plus times OH minus, it gives you 1.0 times 10 to the negative 14, right? So if you're dealing with water itself, a neutral water, its K is going to be 1.0 times 10 to the negative 14 to begin with. And then the H plus and the OH minus will be equal to 1.0 times 10 to the negative 7. So if your A minus is much weaker than the H2O, the conjugate base is much weaker than then you're dealing with a conjugate of a strong acid. And if you have your conjugate base stronger than H2O, which again, it doesn't take very much because the H2O's Ka is 1.0 times 10 to the negative 14, you have a weak acid. Just some stuff that you should have. I'm going to slide all the way through right now, and let me go over here. We're going to go up. I'm going to actually skip 14 point 8 right now in salts. I'll come back to that in a minute. I want to go to 14.9 to start off with. Okay, so let's do this. So here's essentially what we want. We want to have the hydrogen, and I'm going to use the term acidic hydrogen. So let me show you something really quickly. So if you see on this page right here, see how the hydrogen's attached to the main body of your compound. So hydrogen attached to chlorine, hydrogen attached to bromine, hydrogen attached to iodine. There could be many more things over here, but we call this the acidic hydrogen because that's the hydrogen that wants to leave. So this bond right here, the weaker that bond, the more easily that H can leave. So what we want is we want to have a really, really weak bond. What makes a weak bond? Well, polarity does. So if you talk about bond polarity, you want a difference between your electronegative atom and what's attached to your hydrogen. You want that difference in electronegativity to be great. Why? Because let me point this out to you here. If I have hydrogen and chlorine right here, for example, chlorine is way more electronegative than hydrogen. So electrons that are in this bond will shift dramatically towards the Cl, as will it happen in F, as will happen in Br, and as will happen in I minus. And think of it kind of like a rope that's fraying. If the electron shifts in that bond towards the Cl, what's going to happen is that it's going to become kind of thin. Don't actually write that down because that's not a thing, but it's going to allow this hydrogen to be pulled off a lot more easily. Now, what you should be aware of here is this. If polarity alone, the difference in polarity alone, were what determined how strong your acid is, you would think that HF would be a strong acid. But one of the things you have to be aware of is that it's not just polarity, although polarity does help your bond become weaker typically. It also is how strong your bond is. Now take a look at HF. Because HF is really two very small atoms, that means they're very they're very close to each other and they're tightly held to each other. Well, if you take a look at the bond strength, isn't it 565? Then you take a look at HCl and its bond strength is 427. Well, just because HF has such a high bond strength, it means that that hydrogen doesn't want to pull off very much, and that makes it a weak acid. Even though everything else in the halogen tree, if you take a look at it, chlorine, bromine, iodine, all of those are strong acids. This is the only one that's a weak acid. And by polarity alone, fluorine, HF, should be the strongest of acids, but we really look at the bond strength determines what your acid strength is. Any questions for me here?
No.
Okay, now let me show you something else here. Let's talk about oxyacids. As you might guess, an oxyacid is an acid that has oxygen in it. And typically what we do is we have our acidic hydrogen is attached to an oxygen, and this X right here is the tail end of the compound. That X can be many, many different atoms. Now, what you should know is this. The general rule is this. The more oxygens you have in your acid, the stronger your acid is. And the reason that is because the more oxygens you have attached, the more they pull electrons towards them because oxygens are really, really electronegative. Now, let me show you the next page because it's a little bit easier to see on this. So if you take a notice here, see how this HO, this hydrogen right here, this is what we call our acidic hydrogen. So the weaker this bond right here between the H and the O, the easier for this hydrogen to get pulled off and the stronger the acid. Does that make sense, guys?
Yeah.
Okay. Now, the more very electronegative things that we have on the right-hand side, you're going to have a net pull towards the direction. I'm trying to draw an arrow here. If you can see, it's going towards the right. So all the electrons are going to move towards the right-hand side, including the electrons that are in that bond. And when that happens, it's going to essentially weaken this bond more and more and more and more. So if you can see here with HClO4, and you probably have maybe not seen perchloric acid before, but that's one of the 6 strong acids. And if you take a look, its K value is what we like to call large. In other words, this hydrogen wants to leave insanely. Now, if you just take a look at HClO4 versus HClO3, the only difference between these two is 1 oxygen. But that one oxygen is one less oxygen that's pulling electrons towards it on this side. Again, let me remind you that the greater electronegativity atoms always pull electrons towards them. And the more you have grouped up on the right-hand side here, like this right here, the more electrons are going to be pushed or pulled towards this direction. And the weaker this bond is going to be between the acidic hydrogen and the oxygen. That makes your acid stronger, because the weaker your bond is, the more likely the hydrogen is to leave. The more likely your hydrogen to leave, the stronger your acid. Now, if you compare just these two, you're talking on a factor of 10 million times greater K for HClO4 versus HClO3. What does that mean? Well, it just means that we have a much greater pull from the extra electronegative oxygen that we have here than we do here. If you take a look at HClO2, it's even less so, because the O right here is pulling, only one O is pulling here versus two. And if you take a look at HOCl, its Ka value is actually really low, 10 to the negative 8. Why? Well, yes, oxygen is very electronegative, as is chlorine. So they're going to pull electrons. Again, my overall dipole arrow would still be heading towards the Cl in that direction. But the Cl is not going to pull as many electrons towards it from the HO bond as these other two will. Now, let me point out another one. This is one that pops up all the time, and I want you to be able to see it so you understand how it looks in case you ever have to draw it. This right here is H2SO4. You probably recognize that as one of the 6 strong acids. When we do CBS-PIN, this is sulfuric acid. Now, this oxygen right here, this oxygen hydrogen, this hydrogen is your acidic hydrogen, which means that everything else over here is pulling electrons away from that, making this more and more weak and allowing this hydrogen to dissociate almost completely. Now, let's just pretend for a second that my mouse is covering up the hydrogen. So we've lost the hydrogen. That compound, in case you're wondering, that now is HSO4 minus. Now, if I've already gotten rid of this hydrogen, isn't this the next hydrogen that's going to want to try and leave? Now, if I try and get this hydrogen to leave versus this hydrogen right here, once we've pulled off one hydrogen, now this hydrogen is going to be held that much more tightly, and it's not going to be as easy to pull it off. Is everyone okay with that idea?
Yeah.
And if you compare H2SO4 to H2SO3, there's just, if you take a look at this hydrogen right here where it's trying to pull off this acidic hydrogen, we only have 3 oxygens that are and a sulfur that are pulling electrons towards it versus 4. That makes a difference in how weak this bond is. And similarly, if you look at HNO3, that's a strong acid. HNO2 is a weak acid. Why? HNO3 has 3 oxygens altogether, but there's 2 on this side, and it pulls everything this direction and has a very large Ka, aka everything dissociates. Whereas HONO, your K is only 4.0 times 10 to the negative 4. Yep. Okay. And this kind of just shows you in general, just so you can understand how polarity impacts us. If you compare HOCl, HOBr, HOI, or HOCH3, and you're on your own trying to determine which one of those would have a higher Ka, which one would dissociate the best, well, Cl has a higher electronegativity than Br, I, and C, which means, quite simply, that this Cl is going to help the O pull electrons away from the HO acidic hydrogen bond more greatly than these will. And it kind of plays out because you can see how the Ka for this is -8 versus -9 versus -11. And part of the reason that this is only -8 versus -9 isn't the electronegativity difference between Cl and Br very small, 3.0 to 2.8. So that kind of shows you how the Kas are fairly close to each other. Any questions?
No.
So the greater the electronegativity difference, or the more polar your molecule is, the stronger acid typically is. Where that doesn't come into play is when you have a much smaller molecule and the atoms are actually held more tightly together because they're closer to each other, like, for example, HF versus HCl. Okay, let's go back right now to 14.8. This is kind of tricky, although you could kind of learn this without really even understanding. You could be able to do this. So I'm just going to walk you through it. So we're going to talk about ionic salts or salts. Now, all a salt is just a fancy word for an ionic compound. That's all it is. So if I tell you that I have a salt, I'm just meaning that I have a positive and negative ion together. Because we've gotten used to table salt, we typically talk about salt as being NaCl. But from here on out, the terminology, the lingo, allows us to say that salts are any ionic compound. Now, the other thing you need to be aware of is this. When we throw a salt into water, it'll break up into its ions, positive and negative ions. And those positive and negative ions can act as either as an acid or a base. Whichever one is stronger, the acid portion of the ionic compound or the basic portion of the compound, that will determine whether or not you have an acidic solution or a basic solution, which makes the salt acidic or basic. Now, it is possible to have both of these have equivalent levels of acidity and basicity in your compound, in which case we have something that is neutral. Let's take a look at this. So, oh, hi. Hold on one second here. Audra or Amy? There's someone at the door. You guys hold on for 1 second here because I cannot get up from my seat.
Right.
And good that I have this on. Hold on a second here. I'm going to have to holler upstairs or something because evidently everyone's taking a nap in the house except for me. 1 second. Sorry.
Mm-hmm.
I'm back with you here. Sorry. Are y'all with me again?
Yeah.
Sorry, I apologize for that. I'm sitting in my living room and everyone else in my family is asleep, including my infant, and someone came to the door, and that makes it kind of hard since I cannot move. All right, so let's take a look at this really quickly. So if you have KCl, the way I look at it is this: if I threw that into water, what would it try to become? So Cl, theoretically, wouldn't it try and become HCl? And K, wouldn't it try and become KOH?
Yeah.
So what we look at is this. What is the likelihood of those things becoming that? And the likelihood is almost nothing whenever you're dealing with a strong acid or a strong base. So for example, Cl, and another way of thinking of it is this. Isn't Cl minus the conjugate of HCl? So we put an H in front of the anion, and if the thing that it is, the conjugate is a strong acid, then this is going to be a pathetic little base. This K is the conjugate of KOH. Well, KOH, isn't that a strong base? So that means this K is going to be a pathetic little acid. Now, it's hard to think of K plus as an acid. That's one of the definitions we have for acids is a Lewis acid, which we've not yet gone to yet. But if I do this and I have Cl minus will do nothing in water because it's the conjugate of a strong acid. So it's going to create a neutral solution because it's not going to react with water at all. K, when presented with OH minus, it's not going to do anything either. So you have two neutrals that are doing nothing. So overall, if you have the conjugate of a strong acid and a conjugate of a strong base, you're going to end up with a neutral solution. Similarly, if you look at NaNO3, if you throw them into water, NO3, if it were to come in contact with an H+, would it react with it? No, because HNO3 is a strong acid. So NO3 minus is actually the conjugate of a strong acid, which means that it is pathetic. it is such a pathetic base that it is a neutral thing in solution in water. It won't react with anything in water to do anything. Similarly, Na is the conjugate of NaOH. So the way we kind of look at this is just put an OH next to the thing in the front and an H plus in front of the thing at the back. And we see if what they're conjugates of is a strong. If they're conjugates of a strong, then this is a really, really weak, and both these are going to produce a neutral solution. Now, how is that different than this? Well, let's take a look at NaF. So would you acknowledge again that Na, isn't it the conjugate of a pathetic, isn't it a conjugate of a strong base NaOH? So wouldn't Na plus by itself be a very pathetic acid?
Yeah.
Conversely, F minus, it's the conjugate of a weak acid. Well, if that's a weak acid, then this is going to be a weak base, which means this F minus, if you were to let it throw it into water, wouldn't it produce OH minuses because it's a weak base? So what we have is we have a neutral and we have a weak base. Therefore, we have overall, I forgot lost my train of thought. Overall, we're going to have a basic solution. Similarly, let's take a look at this again. So the easiest way to look at this is to think of what would this be a conjugate of if I put an OH next to it? What would this be a conjugate of the acetate if I put an H with it? So if I look at K and I put an OH with it, wouldn't K plus be the conjugate of a strong base, which means that K plus is a really pathetic weak acid, which means it's not going to do anything in water. C2H3O2, that's acetate. It's the conjugate base of a weak acid. That means that this is a weak base. Well, if it's a weak base, it will react with water to produce OH minuses. So therefore, this is a basic salt. So long story short, what we're going to do is we're always going to look at the two ions, the cation or the positive ion, and the negative ion or the anion, and we're going to see what they're the conjugates of. If they're ever the conjugate of a strong, they're going to do nothing. If they're ever the conjugates of a weak, then they will actually produce whatever they are. So if this is a conjugate base of a weak acid, then this conjugate base will produce OH minuses, which makes this a basic solution. Any questions?
No.
We can flip it if we take a look at this. So if you take a look at NH4Cl, same exact deal, right? So let's pretend that Cl, if we put an H in front of it, wouldn't Cl minus be the conjugate of HCl? Well, isn't HCl a strong acid? So wouldn't Cl minus be a pathetic little base that would do nothing? Which means that the Cl minus produces neutral. Let's look at NH4. Well, isn't NH4 plus the conjugate of NH3? And isn't NH3 a weak base? Which means that NH4 plus is a weak acid. And that weak acid, if you throw it into water, won't it produce H pluses? So wouldn't this be an acidic side right here and a neutral right here? And if you have an acidic and a neutral, then overall you have acidic salt. Any questions?
No.
Even if you don't understand the theory behind it, you can kind of just look at the two of them and determine what they're the conjugate of. And if they're the conjugate of a strong, they do nothing. If they're a conjugate of a weak, then they plant their flag on the opposite thing and try and make it either basic or acidic. Now, this right here is a really good diagram that kind of walks you through everything here. And if you compare this, if you have a neutral cation, neutral anion, in other words, if these are the conjugates of strong, conjugate of strong, you end up with a neutral solution. And the example they gave here is this Cl minus, wouldn't that be a conjugate of the strong HCl? And Na, wouldn't it be the conjugate of the strong NaOH? Therefore, neutral, and overall your salt, we consider this to be a neutral salt. Well, then if we take a look at NaF, again, we have the conjugate of a strong, and we have the conjugate of a weak acid, making this a weak base. Well, if this is a weak base and this is neutral, and remember, every time that we have the conjugate of a strong, we're just going to call it neutral. And that means that all we have here is a base left by itself in the salt, and that base, if you throw it in the water, will produce OH minuses, and that'll make this a basic salt. Similarly, the same but opposite. Isn't this Cl minus right here the conjugate of a strong acid, which makes this a pathetic base? This NH4 is the conjugate of a weak base, making this a weak acid. And let me remind you, the conjugate of a weak acid is a weak base. The conjugate of a weak base is a weak acid. The only time that you can you have a conjugate acid-base pair and one of them is a strong is if you're dealing with one of the 6 strong acids, CBS pin, or one of the strong bases, 1 strong Calbert. Lastly, let's take a look at these 2 right here. And this is actually kind of a big deal. So let's say I have SO4 2 minus. Now, SO4 2 minus, do you guys realize that SO4 2 minus is the conjugate of HSO4 minus, not H2SO4? H2SO4 is a strong acid. HSO4 minus is a weak acid. So do you understand that? And again, this would be helpful to draw on the board, but if I compared SO4 2 minus, its conjugate would be HSO4 minus. Well, HSO4 minus is a weak acid, making this a weak base. So wouldn't this weak base want to produce a basic solution? Conversely, Al, if we put Al with OH, wouldn't that be ALOH? Well, ALOH is a weak base. It's not part of CBS, it's not part of 1 strong Calbert. So that means that aluminum is actually a weak acid. So watch this. That means we have a weak acid conjugate and we have a weak base conjugate. Well, if I have a weak acid and a weak base conjugate, the question is it both? This is going to want to produce H pluses. This is going to want to produce OH minuses. So which one does what? Or which one wins? Well, it has to do with your Ka or Kb. Whenever you have both a weak acid and a weak base ion, whatever one has a larger K value wins. So if the Ka value for aluminum is higher than the Kb value for SO4 2 minus, then Ka, the acid portion of it, wins, and this is an acidic solution. If the Kb is greater than the Ka, then the SO4 2 minus portion wins, and this becomes a basic salt. Any questions?
No.
Okay. And this kind of just shows you here. There was someone was knocking on the door for like 3 minutes, and I left the package. So if you take a look here, this just in words says if your Ka is greater than your Kb, if your Ka of your acid is bigger than your Kb of your base, then your then you're having acidic salt. If your Kb is bigger than your Ka, blah blah blah. This is just a picture of that. Oh, by the way, if I look at those 2 right there, acetic acid and cyanic acid, which one would have a greater Kb?
The first one? Yeah.
Which one would have a greater Kb?
The second one?
Yeah, so remember, the stronger your acid, so the bigger your Ka, it means the stronger your acid. 10 to the negative 5 is stronger than 10 to the negative 10. That means that my Ka is going to be stronger than my Ka here. Therefore, its conjugate will be weaker than the conjugate here. So in this case here, we know that Cn minus would actually be a stronger conjugate, stronger base than C2H3O2. Yeah?
Yeah.
And they actually show you, they just wanted to actually have you do the math, and they slowly showed out there. Okay, so let's take a look at this here, and just take a moment while you look at the screen and see if on your own you can rearrange these from worst to greatest. You might have to look at a Ka-Kb table.
Yeah. Less than 7 because it's acidic.
So they just say, this here is kind of a weird thing because they're just saying what is 1 molar solution of each of these. So at the very beginning here, do we have any strong acids?
What did you say?
Do we have any strong acids here in this group?
HBr.
HBr is a strong acid. So wouldn't that produce the lowest pH of all of them?
Yeah.
And on the other side, don't we have NaOH, which is a strong base? So wouldn't that be on the far other side?
Yeah.
Then we look through and we look at see which one of these here could have the stronger Kb or stronger Ka. Now with these right here, let's take a look at NaCN and NaCl. Would you acknowledge that NaCl isn't that the conjugate of a strong acid and a strong base? So wouldn't this be neutral?
Yeah.
But if you looked at Na and Cn, isn't this going to be neutral Na? But isn't Cn minus going to be a conjugate base? So wouldn't this be basic?
Yeah.
So this is going to be more basic than this is. Agree?
Yeah.
And the question though is, what is the Kb of Cn versus the Kb of NH3? Because NH3 is just a straight weak base, just like Cn minus is a weak base. So whatever one has a higher Kb, either Cn minus or NH3 will have a greater pH. Similarly, if you take a look at HF and HCN, if you look at HF and HCN, whichever one of these two has a higher Ka value will give you a greater pH. Any questions on any of how they arranged that?
No.
Hey, Pichon. Hey, hey, mijo. My little boy just woke up from a nap.
Oh.
He's uber cute. I may be biased. Okay, so this is kind of a type of problem that you might face. I'm not going to I'm not going to have you do any more of these. So coming back to me here. Okay. Hi. So, Mr. Ambiel, I believe, gave you the homework. That homework is going to be due on Thursday. So the stuff that we're doing right now, this is stuff that you're working on in class. You'll work on it for the next few minutes here. Hopefully it made sense. These tend to find their way into like multiple choice type questions, like especially ones on the salt strengths and whatever, and comparing them. I could see that. The worksheet that you guys are going to do for homework for tomorrow is kind of based on the stuff. You guys did 15.2, correct? The outline for today?
15.5.
Sorry, the 15 point, which was the one on the indicator one, right?
Yes.
Okay, 15.5. I want to create a folder really quickly that you guys can put your stuff in.
Okay.
You guys can just drop it down and I'll share it with you. Just give me 1 second here. So I'm just going to call it AP B1 2017. And I'm going to give you, I want you guys to all drop your, I'm going to share it with you. Okay. I just sent it to you. I want you to drop your 15.5 outline into that. You should have just gotten an email. And your homework is going to be, I'll show it on the screen. Okay. I'm sharing my screen with you, or am I not? Can you see what's on my screen or no?
No.
Okay, let me share really quickly. This is the worksheet that is actually going to be due for homework for tomorrow. We're kind of backtracking a little bit. It's this worksheet right here. It's called Acid-Base Titration Worksheet. I actually given you the answers for it as well. but it's problems 1 through 10. It's all on. It asks you to do some indicator work, and then some basic plotting, titration, graph stuff. So this is kind of like the lecture, the worksheet that could have been done right at the end of the last class period, but I wanted you guys to look a little bit at indicators first. So this right here, acid-base titrations worksheet, that is your homework for next class period.
Okay.
And let me stop broadcasting now.